Okay, in this lecture, we will understand the small signal analysis. First, we will see in principle what is a small signal analysis, and we will see how to do small signal analysis of the Zener diode and also the normal diode. So let's try to understand the basic principle. What does this small signal analysis means? So consider I have some block here, some circuit here, and this is my input and this is my output, and you know suppose this is the characteristics of this block. So this is my V out and this is my V in, and suppose this may be the characteristics of this whole block. Okay, so it may have some non-linear kind of response. Okay, now if you observe this portion, basically from this region to this region, it is like a straight line, and we can approximate. Suppose let's consider this point here, and if I draw a straight line through this point, right? So I can approximate this whole thing with a straight line, and let's assume I can do the differentiation here, and I can estimate the slope. So I can do a differentiation at this point, which is my dV out by dV in, okay, and I can get my slope m. Okay, so now if my signal is varying around this point, what I mean is I'll be fixing the V in here, and I'll be varying my V in around this point. So this is my delta V in, and my delta V out, the corresponding V out, which will be coming here. Basically this is my delta V out, the change, right? I can easily find out by multiplying with m, right? So what I mean is my delta V out is equal to m times delta V in. Okay, so if I just want to find out a small change in the V out for the small change in V in around this point, then this kind of analysis is called small signal analysis. And this point around which I am changing my input signal, this is called the bias point. I have biased my whole thing at this point, and I am varying the input around that point. So this is also sometimes called as the bias point, sometimes called as the quiescent point or Q point, okay, or sometimes it's called the DC operating point. Okay, so this is what we are going to see. Okay, so this kind of analysis we are going to use for the diodes, as well as when we will be discussing the transistors, we will be doing this kind of analysis, and we will be visiting this concept. And of course here we have to make sure that my input is restricted from this point to this point, right? If it goes out of this point, then this approximation will not hold, because you can see here this is a non-linear region, right? It can not be approximated with a straight line. Similarly, I have to make sure that my output is not going beyond this range. Okay, so this is what we are supposed to make sure when we are doing the small signal analysis. So let's try to do a small signal analysis for the Zener regulator. So again, why the small signal analysis is required for the Zener regulator? Okay, so what we have seen is so this is my V out, and let's call this voltage at this as V in, and this is a resistor R, and we have seen that the input to this regulator is maybe something like this, right? Triangular wave going from maybe let's call 10 volt to 8 volt, going from 10 volt to 8 volt. And here what I want to know is, of course, if this is Ideal, this is ideal. If it is an ideal Zener diode, then it will be something like this. But we know that it is not like this. We have a constant, we have a slight slope, and it is represented by Rz. And depending upon this Rz, of course, in the output also, there may be some small ripple, okay, small ripple at the output, okay, but because this will be very, very small, negligible, it may be few millivolts. So we want to estimate, so given this ripple, how can I find out the ripple at the V out? So this is my problem statement. So one way to do is I can do all the analysis. I can find out what is my V out when my input is at 10 volt, and again I can do the calculation of my V out when the input is 8 volt by solving simple KVL and KCL equation. But we don't want to do that. We want to go for some simpler method, which is also called the small signal analysis. Here we want to treat this like a small signal, and we want to do the analysis. So when we are doing the small signal analysis, we have to be little careful with the notations. So this V in, you can see here, I can split this into two components. One is the AC time varying component and the DC. So what I mean is, if I have some signal like this, which is varying from 10 volt to 8 volt, I can represent this as, I have maybe a 9 volt DC plus this small signal, which is varying from, okay, which is varying from +1 to -1, okay. So this is my small AC, okay, small signal or the signal or AC, right? Different terminologies are used, and I'm representing this plus here, okay. So basically this is my input. So this is represented by capital V, small I n, and this DC is represented by capital V, and this subscript is also capital, and this small signal is represented by small letter V, and subscript is also small letter, okay. So we will be using this notation if there is this AC plus DC. So basically what I mean here is this BIN will be equal to summation of capital V IN plus small v in, okay. So this VIN is superposition of this DC part as well as the small signal part, okay. So this is important. And how do we define what is an AC? So here the average should be 0, okay. So if the average of the signal is 0, then I can consider that signal to be AC. It doesn't have a DC component, okay. Yeah, so considering this notation, let's proceed ahead. So I want to know what is the small change. What is the basically this small v and I in for this one, okay? Given that this is the what is the small v and out for this one? Given that small v I n is going from +1 to -1, okay? Okay. So now for time being, let's remove this RL for simplicity, and we will come back and we will include this RL later on. So now the current flowing through this Zener diode, we know that it is IZ, okay? And I can represent IZ as, IZ is equal to, if I solve a simple KVL here, it is basically V in minus VZ0 by R plus RZ, okay? And now I can represent my V out as capital V out. Again, this has both the AC and the DC, okay? Is VZ0 plus I small z. Again, this has both the AC and DC, okay? So therefore implies my V out will be equal to VZ0. I can substitute this IZ as V in minus VZ0 by R plus RZ and RZ, okay? So implies my V out will be equal to VZ0 minus this will be Rz Vz0 by R plus Rz plus Rz by R plus Rz V in. So now if I differentiate my V out, so what I want to differentiate my V out with respect to V in, basically I want to find out what is the change in the V out with respect to change in V in. Basically I'm trying to find out the slope, okay? So now if you see here, this term will become 0 because it's a constant. This also will become 0 because Vz0 is a constant, it's not varying with the V in. So finally what I'll have is Rz plus Rz by R plus Rz, okay? So, or we know that this is small v out by small v in is equal to Rz by R plus Rz, implies my v out will be equal to Rz by R plus Rz into v in, okay? So now if we look into this expression, this is an expression of a voltage divider. So what I mean is my V out, small v out, small v in, this is Rz and this is R, okay? What we can observe or what we can learn from this is, if I have some DC voltage, something like this Vz0, we can simply eliminate it when we are doing the small signal analysis, okay? We can simply eliminate this part, okay? If there is a constant voltage, we can still simply eliminate it and we'll get this kind of V out is equal to Rz by R plus Rz. So this is the small signal analysis. And of course, if we consider the RL, I just need to add in parallel to this, okay? And the analysis becomes very simple, okay? So the RL will just come in parallel to this RZ and I can find out V out. Whereas if we would have considered the traditional approach that finding out the V out when the input is 10 volt and finding out the output when the input is 8 volt, then things becomes complicated. But when we do this kind of analysis, when we only consider the change, which is basically the small signal analysis, then we can come to this kind of simplified analysis. So the conclusion here is that if I have any DC voltage, something like this, VDC, in a small signal analysis, it will get just shorted, okay? Why? The reason is because when we do the differentiation, this DC voltage becomes 0, right? Anything constant that is becomes 0. So now one may ask, what if there is a DC current source? What will happen to that? Okay, we also can do a similar analysis. I will leave this for you. That what you can do is you can add a voltage source here, right, along with the so you can add a current source here along with the voltage source. So I have my Vz0 Rz R, and you can add an IDC and you can try to find out the differentiation of this V out by V in, right? What you'll observe is that this IDC also will become it will become an open circuit. So in case of the small signal analysis, if I have my DC here, IDC, right, you will see that this will become an open, okay? I'm not doing this one. You can try it yourself. It's very easy. So you can just write simple KCL, KVL expression and try to express this V out in terms of V in and just do the differentiation. You will observe that you will come to the same expression like this one, where this voltage source will get sorted and this current source or the constant current source DC will become an open. Okay, this was the small signal analysis when we are talking about the Zener diode. Okay, so let's try to understand the small signal analysis if we are given a diode circuit. Okay, let's consider a very simple diode circuit. Okay, so maybe we have this input VIN, okay, which has both the AC and the DC component, okay, and we have a resistor here. This is my ground, and this is my resistor R, and this is the V out. Okay, so of course we can decompose this into two parts. We can decompose this V in into two parts as the small change, which is indicated by small v and small in, and I have the DC part, which is basically the capital V and in. Okay, so in case of the diode, first what we will do is we will try to find out the DC current only. Okay, we have done that. We have solved diode circuits, and there what we did is, given a DC source, what is the DC current, and we have done it by using this constant drop model. Okay, now we want to find out, suppose there's a small voltage that is riding over, we will not be able to use the constant drop model, because if there's a constant drop model, the V out is constant with this 0.7 volt. But we know that in case of a diode, the diode has a finite slope. So if there's a small change in the diode voltage, or we can see change in the diode current. Okay, so this is what we want to see using this small signal analysis. So let's try to just do the constant drop model first and try to find out the DC current. Okay. Okay, so I have approximated diode with a 0.7 volt drop. Okay, so now I can find out my current ID, DC current basically. So my ID will be given by V in minus 0.7 by R. Okay, so here note that the current across this diode is defined by this V in and R mostly. So let's consider an example. So suppose my R is 1 kilo ohms. Suppose my R is 1 kilo ohms and V in maybe 3 volts. So it is 0.3 minus 0.7. It is 2.3 milliampere. Okay. Of course, we have approximated this to 0.7, so it may be 0.75 or 0.65, but you can see here the variation will be very small if there is a variation in this 0.7, right? So I can say that it can go from 2.2 to 2.4, right, at max. So, but it is mostly in that range. So what the important point here is, the diode current is mostly defined by this resistor and this V in. Okay, so this is what the diode is defined mostly by this resistor, right? If the resistor instead of 1K, it is 10K, then the division will happen and it will be 10 times smaller. Okay, so the diode itself is not defining the current. Okay, because if you are considering this model, what we have considered is that the voltage across the diode is 0.7, and this is my current across the diode, and this is the voltage VD across this diode. Okay, so if you see here, if you see this slope, it is not defined, right? The current is not defined by this by this model. Okay, it is not defined. The current is mostly defined by this resistor. So this is an important point. Okay, so now given that the current is defined by the resistor, now if we come back to this diode equation, okay, so if you come to these diode characteristics, let it be let me call the current through this diode as ID, and this is as VD. Okay, it has both the small signal as well as the DC. Okay, and we know that the diode current rises exponentially. We know that this ID is equal to Is e power Vd by Vt. Okay, this is the expression. Okay, so now, as we have mentioned, this diode current ID, the DC current is defined by the resistor itself. So this ID, right, the DC current is defined by the resistor. So this is my solution point. Okay, and what I want to do now is, suppose, because now my current is defined, so what I can do is I can draw a slope here, okay, around that point, right? And what I can do is, if I know this slope, right, slope of this line, if there is a small variation in my VD, I can find out what is the variation across this ID. Okay, if I know the slope. So this kind of analysis is called a small signal analysis. So by using the resistor and all, we have defined the diode current, and then if we want to know if there's a small variation across this voltage, of course here we are fixing it as 0.7, but suppose if there's a small variation, how is the diode current going to get affected will be defined by this slope. Okay, so let's consider this slope, right? The slope in this case is called 1 by RD. RD, because if you see here 1 by RD, because I'm having this relationship between the current and voltage, right? So in this case the slope will be delta ID by delta VD, right, which is inverse of the resistance. So I want to find out this, and this small slope RD. So with this I will be able to find out if there's a small change in my this VD. So we can call it as small v and d, and this change in the diode current as this one as small id. So if I know this slope, then what I'll be able to see is that my this vd will be equal to id into rd. So this is like a simple Ohm's law, right? This right, my change in my this, or my change in my current is basically Vd by this Rd. Okay, or my change in voltage, if I know the change in the current, is given by Id into Rd. It's basically like the Ohm's law, V equal to IR. Okay, so let's try to find out what is the slope at a DC voltage or at a bias voltage of ID. Okay, so now if I rewrite this equation, this is what I'm going to get, that my ID is equal to Is e power Vd by Vt. Okay, so this has both the DC and the AC. So let me decompose these two components. So this ID, I can write it as capital ID plus small id, okay, is equal to Is, which is basically a constant. There is no signal writing over it, and e power this Vd I can split as Vd plus small vd by Vt, and I can write it as Is e power Vd dot e power small vd by Vt. Okay, so Vt term also will come here, and this whole term is nothing but the id. Okay, right, because for a voltage Vd, my current, the DC current that is flowing, right, for a DC voltage Vd, the DC current flowing through this diode is id. Okay, this basically this id for a DC voltage Vd. Okay, so implies my id plus small id will be equal to this id e power Vd by Vt. Okay, now let's assume that this change is very small. If my change Vd by Vt is much lesser than 1, we know that we can approximate this whole thing it is an of the form of e power x, and we know that e power x can be approximated by 1 plus x if the x is much smaller than 1. Okay, so if I substitute this approximation, like this id is equal to 1 plus vd by vt into id. Okay, and if I just expand it, what I'll get is id plus small id equal to id plus id vt into vd. So what I can do now is I can cancel this one and this one, and finally what I'll get here is my id is equal to this id by vt into vd, or I can write it as vd by rd, where my rd is given by rd is equal to vt by id. Okay, so this is an important conclusion. So what it means basically is that if I have found out this ID or the point or the solution point or the ID or the DC operating point, then I can find out the RD by dividing VT with this ID. Or in other words, if this ID is fixed, right? If this ID is fixed, then, or I can find the slope of this curve by dividing this ID with a VT, or which is the inverse of RD. Okay. Okay, so now the next question is, how do we do now the small signal analysis? Okay, so small signal analysis, as we have noted, we can omit all the DC component part, and we need to include that small RD here. Okay, so basically in this diode, in this situation, we have to replace this diode with the small signal resistance. Then we will be able to find out what is my V out for a small change in the V in. So finally, this is what I'm going to get. So okay, so this is the small signal model of the diode circuit. Okay, so basically what it means is that here I am looking into the chains. So all my DC voltage will go away, and finally what I will get, my V out, it is a simple division. So it is RD by R plus RD V in. So provided if there is a change in my V in, the V out, change in the V out will be given by this one. So here we are ignoring all the DC components. This is very important, that first we are doing the DC analysis, and we are calculating the slope or the resistance, right? And then of course this R will also include in the small signal analysis, because this R is going to affect both the DC as well as the small signal. So the R is always there when we are doing the DC analysis. This R also will be there when we are doing the small signal analysis. Whereas the DC voltages and DC current source will be eliminated, because that is not going to affect the small signals. Okay. So coming back to our original definition of the small signal analysis, we are doing basically this thing, okay? So we are biasing our circuit at one point, and then we are estimating the slope. In this case, it is RD. And then we want to see what is the variation in the y-axis for a given variation in the x-axis. So the other way to look the small signal analysis is basically, this is my point, biasing point, and here what I have estimated my slope. And because we are ignoring this DC part, it is basically we are shifting this the origin, okay, to here. So basically what it means is, I have my new set of x and y axis. This is my small vd, and this is my id, right? So, and this is the, basically this is the line, this line, and it has a slope of 1 by rd. Okay, so what we want to see here is, if there is any change, if there is any change in the vd, what is the corresponding change in the id, which is defined by the slope. and it is given by Vd equal to IDR. So this is the relation. Okay, so if I want to know my ID, I just need to divide this Vd by Rd. Okay. Okay, so this is the main principle of the small signal analysis, where we are linearizing the variation. Basically, we want to just linearizing the whole thing or approximating the whole thing with a straight line, because what we have assumed is that the change is very small. Okay, so in this case, we have approximated the Vd to be much smaller than Vt, and Vt we know that at room temperature is 26 millivolt. So we can consider this Vd to be varying maybe 5 millivolt, or 6 millivolt. Okay, so of course here the analysis here is not much complicated in case of the diode, but when we will be discussing about the transistor, we will be coming back to the same analysis and we'll be using this conclusion that we have used for the diode. Okay. Okay, so before we go ahead, let's try to solve a small problem on this so that the concepts and the understanding of this one becomes very clear. Okay, these are my two diodes, D1 and D2, and it has two resistance, R1 equal to 3.3 kilo ohms, and this R2 is equal to 5.6 kilo ohms. Okay, and I have a V in, V capital V small I in. So basically it has the both the DC and the AC, 20 maybe plus minus 1 volt, and we want to know the output V out. Of course, this is also a combination of the DC V out plus small v in, and of course we have the ground here. Okay. Okay, so we have solved this similar problem, this same problem for just getting the DC value. Okay, but here what we are going to do is that, you see, this my V in is, of course, it's 20 volt, the DC is 20 volt, but on top of that there is a small signal which is plus minus 1 volt. This is the small VIN, and this is the DC which is capital VIN. Okay, so I want to know what is this, of course I want to know what is this DC value also, and I want to know what is this small change. The first thing that we are going to do is we are going to do the DC analysis or operating point analysis. What it means is we just want to find out the DC currents flowing through all the diodes. This is same as whatever we had done before. Okay, so let's do that one. So this is my circuit. So consider the DC voltage here. Okay, a 20 volt is applied here, and I want to know what is the current flowing through this diode D1 and D2. For that, of course, we need to approximate this diode with a DC voltage drop of 0.7 volt. Okay, so now let's try to evaluate the currents. The current flowing through this one is, let's call it as IR1, this as IR2, and the current flowing through this one as ID1, and the current flowing through this is ID2. Okay, so IR1, we know that IR1 is basically given by the voltage drop across this resistor. This at higher and this at lower is 0.7. So 0.7 by this R1, which if you put 3.3, then it is IR1 is 0.21 milliampere. IR2, if we do simple KVL of this loop, right, the total voltage drop across these two resistors, if you see this 20 volt, minus 0.7, minus 0.7, so 20 minus 0.7 minus 0.7 by this resistance R2, right, it is 3.32. Okay, and of course this is the IR2, and this same current is flowing through ID1. So this is also basically this ID1, okay, and we know that this IR2 is summation of ID1 and IR1, summation of ID2 and IR1. So implies my ID2 will be equal to IR2 minus IR1. So it is 3.11 milliampere. This also milliampere, okay. So now I know the current flowing through this diode D1 and diode D2, and here you can see here it is mostly defined by these two resistors, okay. So therefore the resistance offered by this first diode, which is RD1, is equal to VT by ID1. So this is the resistance offered by the this first diode to the small signals. So which is basically, if you consider this as 26 millivolt, so it comes out to be 7.8 ohms, and RD2 will be VT by ID2, and if you consider again this as 26 millivolt and do a division, you will get 8.36 ohms, okay. So now these are the resistance offered to the small signal, okay. So now we can easily draw the small signal circuit and we can find out the change in the V out. So the circuit will look something like this. So now we will do the small signal analysis. So for that case, I need to replace this diode with a small resistance. This is RD1. This will be RD2, okay. And of course, this here only will have the small change V in, and here only the small change V out, okay. And of course, we know that if you see here, finally, if you see this is can be easily simplified. These two resistance are coming in parallel, okay. And of course, because this RD2 is only 8.36 ohms and this is kilo ohms, so finally we'll have only this RD2, okay. So the equivalent circuit will become something like this. So I have my V in here, this is my ground. Here I have RD1, and here of course R1 parallel RD2, but it will be approximately equal to RD2 only because RD2 is very small. And of course here we have this R2, and here I have my V out, okay. So I can easily write, therefore my V out is a simple voltage division, which is basically R2 into V in by RD1 plus RD2 So finally, this will be the expression of my V out, and I can find out the change in the V out by just substituting these values, okay. So this is how we can find out the change in V out with respect to the change in V in with this type of small signal analysis. Many students have asked this one that okay, I have considered this resistance for small signal analysis, this small RD. Why have I not considered this small resistance while doing the DC analysis? Okay, so basically, if we include this a small resistance, then what would have happened is, instead of we approximating the whole these diode characteristics, so we have approximated the whole diode characteristics with a straight line, right? To make the analysis very simple, right? So instead of approximating with a straight line, if I would have added a resistor, I would have been approximated this whole thing maybe with a uh, with a straight line having a small slope. Okay, so of course this is also possible, right? Because we also have done this kind of approximation when we did for the Zener diode, right? So instead of just making it a fixed a straight line, something like this, we have approximated with a with a line having a small slope. So this can also be done for this diode, but generally because the voltage variation is very small, it's around zero point 0.7 only in case of the diode. So approximating just with a straight line, right, without having a resistance here, makes things much simpler in case of a diode. Okay, so with this, we will end the discussion on the small signal analysis for the diodes.